Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. Okay, I want to explore this uh, abstract with you in a little more detail than what I did in the Sea Ice Melt Explained video, part two. So I talked about this for a little bit in that video. I want to do a bit of a deeper dive with this. Here we go. So again, this is Rebecca Woodgate and her co-author Cecilia Peralta Ferriz. And it was just published in April of 2021 in Geophysical Research Letters. So, what are some of the highlights here? In situ hourly from 1990 to 2019, basically a 30-year period, data show Bering Strait flow increases approximately 0.01 sphere drip per year, which cuts the Chukchi residence time by approximately 1.5 months down to about 5 months, to approximately 5 months now. In other words, it used to be about 6.57 months that the water would sit in the Chukchi Sea. Because of the increased flow rate into the Chukchi through the Bering Strait, it's basically flushing the water that's in the Chukchi, reducing the residence time. Residence time refers to how long water stays in an area. In the spring and fall warming, we see about approximately 0.1 Celsius per year. Now think about it. This is over 30 years, so that's implying that the waters have warmed by about 3 C. When you consider the specific heat content of water, that is a significant amount of warming. So this approximately 0.1 C per year yields monthly means 2 to 4 C above climatology, which refers to basically long-term average values. Warm waters persist for more than 7 months. Previously, it was 5.5 months. So if you have warmer waters sitting there for, persisting for more than 7 months, which is more than half the year, is it any small wonder that the sea ice is disappearing? No, obviously not. Pacific winter water, PWW, is freshening to less than summer salinities. In other words, it's being infused with more and more fresh water, so the salinity is being reduced. So this shoals Arctic ventilation so that the Pacific winter water no longer renews the cold halocline. Okay, what is meant by that? Ventilation in oceanography is a term used to indicate vertical mixing of the water column such that you basically flush out the entire water column all the way down to the substrate. Well, if you have the surface water reducing in salinity, the density is going to be less. You're not going to get that sinking. So what he's saying is that the shoaling basically means it's getting shallower. The halocline is moving closer to the surface. So renewing the cold halocline, that basically is part of the overturning and the mixing of the water column vertically. I describe such mechanisms in my Let's Talk Overturn, Mixing, and Stratification video, which if you have not seen that, you may want to check that out. Okay. I'll go through the abstract and then we'll go look at this again. This is a very important diagram, and as well as this here, although you've got temperature on the vertical scale, salinity on the horizontal scale. It's what we call a TS curve. And we'll discuss that after we go discuss the abstract. So, Pacific inflow to the Arctic traditionally brings heat in the summer, melting the sea ice, dense water in the winter, which that dense water refreshes the Arctic's cold halocline and nutrients year-round, supporting Arctic ecosystems. Bering Strait moorings from 90 to 2019 find increasing about 0.01 plus or minus 0.006 sphere drifts per year northward flow, reducing the Chukchi resident times by about 1.5 months over this period. The record maximum and minimum was about 7.5, 4.5 months respectively. Annual mean temperatures warm significantly by about 0.05 plus or minus 0.02 degrees Celsius per year, with faster change about 0.1 degrees Celsius per year in warming in June and July, and cooling October, November months, which are now 2 to 4 degrees C above average temperatures. Warm, that's greater than or equal to 0 degrees C, water duration increased from 5.5 months in the 90s to over 7 months 2017, mostly due to earlier warming, which is by about 1.3 plus minus 0.7 days per year. Now, you're going to say 0 degrees C. Doesn't water freeze at that temperature? If it were fresh water, yes, but this is oceanic water. Because of the salinity, you have freezing point depression, the water will freeze at temperatures less than 0 degrees C. Typically for the Arctic, it's about minus 1.8 C, given on the precise salinity levels. But the point here is that when you get to 0 degrees C for oceanic water, it's liquid. Dramatic winter only, January to March, freshening by about 0.03 PSU per year. PSU is practical salinity units. Makes winter waters fresher than summer waters. The resultant winter density change is too large to be compensated by Chukchi sea ice processes, shoals the Pacific winter water equilibrium depth in the Arctic from 100 to 150 meters to 50 to 100 meters. Shoals basically means getting shallower, and here we see it, 100 to 150, 50 to 100, basically by a good 50 meters. So this shoaling implies that Pacific winter water no longer ventilates the Arctic's cold halocline at 33.1 practical salinity units. Okay, plain language summary. The Bering Strait is the only oceanic link between the Pacific and Arctic Oceans. The typically northward flow through the strait carries Pacific oceanic nutrients to the Arctic, vital for ecosystems. The flow varies seasonally in temperature and salinity in spring-summer. In spring-summer, it brings warm waters that start to melt back of Arctic sea ice in winter. It starts the Arctic sea ice. In winter, it carries cold waters that traditionally sink deeper, 150 meters into the Arctic, well below the summer waters. Annually, surface instrumentation moored to the seafloor measured hourly. The flow in properties in the strait from autumn 1990 to summer 2019. We find the flow is increasing significantly, reducing by about 1.5 months the time taken to reach the Arctic from the strait, which is now 5 months. Summer waters are now 2 to 4 degrees C warmer than typical in the 1990s, and warm for longer, 7 months compared to 5.5 months. That extra month and a half means a lot. In winter, waters are dramatically fresher than before, now fresher than in summer. This change means the winter waters can no longer sink so deep in the Arctic, now only 1,500 meters, the same depth as the summer waters. This not only means oceanic nutrients are available closer to the surface, but may also restructure how the upper Arctic Ocean mixes. Now, there's something to be said about this. This is kind of a double-edged sword. oceanic nutrients are available closer to the surface. Closer to the surface, that would improve productivity. Now, as long as this is kept continually to be brought in, so that it replenish the nutrients in the upper layers, then the phytoplankton should have enough nutrients to do their thing. But remember, if we're losing the sea ice, you're losing the productivity from the ice algae on the underside, as well as the productivity from ice edge meltback. You get that little bit of stratification from that freshwater lens that stabilizes very shallowly, but stabilizes that water column and get productivity. You're going to lose those two sources of productivity. So you can have all this nutrient in the upper layers there, but it's not going to mean anything until the sun gets high enough in the sky, a high enough angle that will then activate the phytoplanktons, the diatoms. So if the sun is still low in the sky, all the nutrients is not going to really, it's the phytoplanktons need the sun to be higher before they can start doing their thing. Now, usually, when you talk about ocean stratification, yes, you need the stratification to lock in the nutrients, and then the phytos do their thing, but the nutrients will get used up, and therefore you need a mixing event to replenish that. Well, if you have continuous stratification, eventually you're going to use up the nutrients. Eventually, productivity will start declining until it totally gives out and goes to zero. Now, in this case here, what she seems to be implying is that there's a continuous supply of nutrients brought into the Arctic. If that's the case, then that may indeed help productivity, with the caveat of the angle of the sun. Okay, so he's got some figures here. We'll look at the figures here. I'll start at figure 1. So figure 1 is the annual mean Bering Strait properties. So A, we have summer satellite, MODIS satellite, sea surface temperatures, SST, image of the Bering Strait region showing moorings, which are black dots. And let's see, B is the total northward volume transport estimated from several of the moorings. C, where is C? C is near bottom temperatures with SST in red. We have salinity. H, GI shows heat and freshwater transports. Small print's kind of hard to read. Okay, so let's just look at this here. So here's some of the moorings. So here's the Bering Strait. Here's the Chukchi. East Siberian is over here, right? Chukchi, okay, right through the strait there. And here are sea surface temperatures. You can see a bit on the warm side, on the eastern side of it, cooler on the western side of it. Then here is the transport in sphere drips. And if you look, there's a very interesting dip in, what's that, 2012 or so. But the overall trend is that of increasing and shows the temperatures being brought with it. I discussed this. This was discussed in the other abstract paper that I included in the Sea Ice Melt Explained video. So here's the temperature. Here's that little dip down in 2012. And you can see clearly, especially in the last almost decade, clear increase in sea surface temperature. JD is referring to Julian day, so that's the day of the year. So basically, 130 days, 4 months. So this is getting into May, in essence. And what this is showing is that the trend is starting to decrease. Notice the sea ice amount is decreasing, as well as what day the temperature is greater than 0. So that's on the warming side. On the cooling side, we see what? We see that it's getting longer, later is a better word, in the year. So this is showing that the melting of the ice is getting earlier in the year, right? The freeze up or the cooling down towards freeze up is occurring later in the year. And then this is showing how many days above 0. See, again, you had the interesting dip down in 2012. It's almost an anomalous situation. But when you look at overall, there's more days above 0. So, sum these up. The ice is going away earlier in the year. The ice starts forming up later in the year. There are more days above 0 in the year. That's what these three tell us. I've already discussed, we already showed this, that, the transport in sphere drops is overall increasing, as Rebecca reported. Of course, 2012 shows up regularly through this year, the dip down here. So we see that, and as she reported, about 0.1 sphere drops per year in the summertime, overall about 0.01 sphere drops per year. These three here, we have the heat flux, and let's see, what does that red say? With the ACC 1 times 10 to the 20 joules and the surface layer. Okay, so the ACC is probably the Arctic coastal current, which is flowing, of course, in the Arctic. And the black lines represent the data taken from the moored stations. So we have the heat flux. We can see an overall increasing trend. The middle one is salinity, and we see that it is decreasing. And then the freshwater flux is increasing. Kind of cyclical, but we see that it's increasing overall. And that again refers to, mentioned earlier, that this halocline is shoaling, getting shallower. So we're not getting the sinking, we're not getting the ventilation, we're not getting the turnover. Basically, it's changing the structure of the upper layers of the water. Okay, figure 2. Let's see what figure 2 is. Figure 2 shows trends, recent change in Bering Strait properties at that station A3 in transport, temperature, salinity, density, heat transport referring to the volume of water, freshwater transport, and then G, percent of basically ice concentration. The first column is trend per month. Large squares is significant from 1990 in black, 98 in blue, 2000 in red, to the end of the present data, summer 2019. The last three columns are the 30-day A3 mooring station data for 2016, 17, 18. All prior data is in gray. So these 3 years are in red. All prior data are in gray, with the 1990 to 2004 climatology of ice or water properties. Okay, that's kind of like a reference there, baseline. So what do we have here? So what we're seeing here, first of all, this is for variations within a year. We have January, March, May, June, September, November. And it's basically showing seasonal variations. We see the declining in the flow into the water, picking up later on in the year. We see, and of course, we see the temperature increasing as the year progresses, and we see the salinity and the density tying closely together, as well as what the terawatts, the heat, increasing and decreasing, and the what the fresh water is also decreasing and then increasing later on. This is over the course of a year. Then we get into kilograms per cubic meter per year, so that's density. You will note that the density closely follows the salinity. Remember, in high latitude oceanography, salinity is the more principal determiner of density. Tropical waters, it tends to be temperature. So in high latitude oceanography, density is really more influenced by what the salinity is doing. If you look at a lot of these graphs that show a peak, it tends to be in September. September is the oceanic summer. So that to me tells me that it's not an accident that we're seeing these spikes here. And she addresses that in the abstract with the various statements that she has made. So in looking at these three columns here, we have 2016, 17, 18. The first, and the red is for the given year. The black is the 30-day smooth data, and the gray is basically the average data over the 30 some odd years that this study's been ongoing. So the first line is transport and sphere drips, and we see a spike in basically September. It's a little bit kind of increasing, decreasing, and increasing again for 2017. 2018 kind of shows a decreasing trend overall, so that's kind of interesting. When we get to the temperature, we see a spike basically September, October, November, that time of year, which is, of course, the oceanic summer. And we see a large increase over the summer months that we call terrestrial summers, basically spring and summer months. And the same thing with, again, another spike in September for 2018. So we're seeing this drastic increase in temperature and heat that's being brought in. The next row shows a salinity. And we can see the general trend, the salinity is declining. And not surprisingly, sigma, that's the density, the sigma curve is also declining overall. Again, salinity tends to determine the density in high latitude oceanography. Now take a look at the heat. This is in terawatts, that's 10 to the 12. Look at that spike in September, October. Makes sense. That's this, that's the sea ice minimum. You're going to have a lot of, you're moving in a lot of warm water. So we see that here. So again, we see an increase in heat, looking at here, and then it jumps up. Same thing when we looked at the temperature curve here, kind of low, then jumps up. So we see the same sort of figures here. In other words, it makes sense. The temperature, if it's warming up, is bringing in extra heat. So it would make sense that the heat curve would be rather similar to the temperature curves. Then this is freshwater transport and sphere drips. And 2016 is interesting. We had a really a spike event, if you will. 2018 shows a decreasing trend. So there's something going on with 2018 that is interesting. And then the last one is the ice concentration. And so here's September now. That makes sense. We see a minimum because that's the oceanic summertime. And then it starts building back up as we head into the winter months. So that's what figure 2 is showing. And all these figures here are basically summed up by what is mentioned here in the abstract. So now figure 3. What I want to look at now is D, this bottom one here. This is a TS plot. That's D and E. We'll look at D and E. D is a TS plot, temperature salinity, for 2002 waters north of the Chukchi slope, colored by silicate, which indicating Pacific influence. Okay, based on her research from 2005, marking changes in the temperature salinity of Pacific winter waters, PWW. And then E, we'll get to in a moment, is a schematic of the changing ventilation of the Pacific winter summer waters. So with a TS curve, typically you have temperature on a vertical scale, salinity on a horizontal scale. Water properties, water masses have distinct properties. In other words, we have this salinity, we have this temperature. That would identify this water mass, and that would be a dot on the graph. Where you start seeing the lines, that's where you start seeing mixing. So let's just say, for example, I have water mass A that has a temperature of minus 0.5 C and a salinity of 30. I have water mass B, which has a temperature of minus 0.7 C and a salinity of 29.5. Okay, so you could find those dot boom and identify. But in between, you might see some sort of a curve joining those 2 points there, and therefore you would know that those two water masses have come in contact. They are mixing. So when you see this colored in region here, this is the mixing that's taking place. Now, she was able to identify specifically Pacific winter water in 2014, right at that location there. Pacific winter water in the 1990s. It's in here. So what's the difference here? Well, winter water is less fresh, right? Here's the salinity. It's 30, 34. This is 26 over here. So the salinity went from basically 30, 30.5 or so down to like 28. That's a sharp change in salinity. The temperature changed ever so slightly by about, looks like a decrease of not by about, half a degree C. But when noted changing properties of the Pacific water, this freshening is what refers to in this diagram when she and refers to her statement that the shoaling of the halocline is taking place. It is less salinity. The change in salinity is greater than the change in the temperature. So even though temperatures got colder, the salinity dropped by much, much more, so that the overall density decreased. It did not increase, it decreased. That decrease in density prevents the mixing, prevents the ventilation. It doesn't, and prevents the, not flushing that cold halocline, resulting in that halocline getting shallower. And if that halocline gets shallower, halocline is like a pycnocline, change in density. You're not going to get mixing across that barrier there, so the nutrients would be locked in. So let's look at this diagram here. Pacific summer water in the 1990s was about 0.4 seer drops, going into the Chukchi. Pacific winter water about 0.5 seer drops. In 2014 and onwards of 2019, it increased from 0.4 to 0.7. Pacific winter water stayed the same. That is a major increase. And when you consider how much the waters have warmed up, that is a lot of heat to be continually bringing in to the Arctic Ocean. So if we want to look at the temperature, the temperature was about 1 degree, plus 1 degree C, with a salinity about 32.7. And in 2014, it increased by 3 degrees C. Remember I said that, if you looked up here, let's say she's saying that the temperature Temperatures warm significantly with the fastest change about 0.1 degrees C per year in the warming. Well, over 30 years, that's 3C. Just verified it for us. 1 to 4, that's 3 degrees C. Salinity stayed the same. Now let's look at what the Pacific winter water did. Temperatures about minus 1.9 back in the 90s, still about minus 1.9 in recent years. But look at the salinity. The salinity decreased from 33.5 to 32.1. May not seem like much, but that's a decrease about 1.4 parts. Is subtle changes in salinity, especially at high latitude, that can determine thermohaline flow. So that is significant. So what does this mean here? Okay, she basically put this little model together, and that she's showing layers of the ocean. So go from 0, 50, 100, 150 meters in depth. And this here, this first layer in gray, is basically mixed surface layers. So you've got freshwater input, you got precipitation, evaporation, you got all sorts of mixing in the shallow layers, including wind action. From 50 to 100 is the Pacific summer water. Then we hit the cold halocline layer from 100 to 150, which then all of this sits on top of the Atlantic water layer, 150 meters and deeper. What she is saying is that, and if you look at here, look where she places, right, the salinity here to here. So she basically says that the halocline is shoaling. It went from 150 up to 50 to 100. So it's gotten shallower. And don't forget, on the Atlantic side, you got warm water moving in. All that warm water is going to diffuse upward. It will also contribute to melting the sea ice earlier in the year. So the take-home message from all of this is that the flow from the Bering through the Strait into the Chukchi, into the Arctic Ocean, the flow rate is increasing. The temperature is increasing. So when the flow rate is increasing on a daily basis, yearly basis, that means you're bringing in more and more heat on a daily basis, on a yearly basis. That heat is going to contribute to melting the ice earlier. We're also seeing that the residence time is decreasing. So instead of that cold water lingering for a longer period of time, it's flushed out. It's flushed out sooner, so the residence time is decreased. That warmer water, because of the increased flow, I mean, if you got water moving in, it's got to leave somewhere else. All this warm water moving in, that warm water is now staying longer in the Arctic Ocean by a good 1.5 months. So that it's now the water is warm for 7 months of the year. And warm is basically greater than 0C, which is enough to keep it liquid. So now we've got warm water for 7 months of the year. The salinity is dropping so that the halocline is getting shallower. So you're reducing the ventilation or the flushing, the vertical mixing, so that the cold halocline is not really renewed. It kind of stays in place. This can rewrite the structure of the Arctic Ocean. It would impact and will impact productivity. And I discussed that in the early portion of this video. So that's the essence, the summation of what is being presented here. And with this, if you're shoaling the Arctic aspects, that is going to allow for more Atlantic water to flow in, which means what? You've heard me discuss the Atlantification of like the Barents Sea and the Arctic Ocean in general. This is what's happening. We are Atlantifying the Arctic Ocean. we're changing its properties. It's becoming saltier and warmer. Now, yes, it's becoming saltier, and then you've got less saline, at least in the upper surface layer. So we need to see how those dynamics play out. But with the warmer water being moved in, that warmer water is going to diffuse upward, just as the warm summer Pacific water is diffusing in on over the top of the Atlantic water. That's helping to warm the ice. So is the diffusion of heat from the Atlantic water will also contribute to ice melting. So warm water from the Atlantic, warm water from the Pacific side, all working to melt the sea ice earlier in the year, but also because it's warmer, especially the surface water being warmer, that delays when the ice freezes. It freezes now later in the year. Plus the fact that the surface water is absorbing sun energy, and you have to really cool down the water well below 0°C to start getting ice formation. This is why the sea ice is freezing later in the year and melting earlier in the year. So we're having more open water. It's increasing every year. I will leave the link in the comment section below. You can feel free to click on download the preprint and spend several weeks going over the 56 pages or so of it. Or maybe the other one said 56 pages. But they're lengthy papers, but they're chock full of excellent science and excellent information. So I'll leave it at that. And thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.